Welcome to Cryptography and Hardware, the 7th session. This session we deal with other type of implementation of the AES, which is called column-based implementation, and also talk about some ways to optimize the implementation of the AES Sbox in hardware. The fact here is that you learned already a couple of different implementations of the AES, like the round-based, and also how to use the blockrams, dedicated modules of the FPGA to implement the AES. The fact here is that a couple of years ago, it was not really possible to fit the full AES round base in hardware in the chips because of the area. Nowadays, it's not a big matter, and it's usually possible to do so. But then, how to efficiently implement the AES and how to reduce the area, this is one fact and one point. And of course, somebody or something should be paid for that. For the area means that when we gain some area and reduce the area, we have to pay some penalty, like the energy, or like the latency, or like the number of clock cycles, or the waiting time is higher, and so on. You know, this is always a trade-off. If you reduce the area, something else is higher. And now we see how we can do it for the AES, for example, for AES 128. We see that, and we learn that 4 Sboxes actually are coming to one mixed column, and then all these 4 modules that you see here, which are similar to each other, they can be shared. It means that you can have one instance of these modules, which contains 4 Sboxes and one mixed column instance, not mixed columns, and it's not actually applied on all 4 columns, only on one column. And then share this instance between all columns of the AES or cipher state, and then realize the entire encryption function. Now, this is the idea, and for that you need to also use the Sboxes for the key schedule at the same time, because the key schedule for the G function needs also the Sboxes. Now you can think of, okay, if you have 16 Sboxes and 4 of them also, another extra 4 others for the key schedule, for the area. Now, by reducing this to the column-based implementation, you will have 4 Sboxes and one mixed column, which is actually enough, and it can be also realize the G function of the key schedule. But then you need at least 4 clock cycles for the Sboxes and the mixed column. You can also imagine the add-drone key is done also simultaneously. And then you need 1 extra clock cycle dedicated to the shift rows, because it doesn't fit to this fashion of the column-based operations. But then a good point is that in this clock cycle, when we implement or realize the shift rows, we can use the 4 Sboxes with the G function in the key schedule. This is the idea. Of course, somebody can reduce this as well and say, okay, I have just 2 Sboxes, not 4 Sboxes, or I have 1 Sbox only. And another implementation, which is called also serial implementation of the AES, that we will see next session. This is the concept that, okay, let's reuse some part of the logic. And of course, when you reuse it, you need to reuse it in different clock cycles. And for that, you need to pay latency. Now, how this works, this is the state of the AES, the matrix, 4x4, and where the cipher state is stored. And then, of course, if we have, or if we call the functions to be called, here we have 4 Sboxes, which receive actually these 4 inputs directly from the cipher state. And then afterwards, the output of the Sboxes are given to one instance of the mixed column, which means only 1 column is mixed. And then the output of this mixed column, which is a 32-bit, is stored entirely in this column. It means that everything is actually shifted 1 column to the left, from right to left. And then everything is shifted and one column is updated. And then, of course, 4 clock cycles, the same operations is applied on every column individually. Yeah. Then what we should also consider is that here in this implementation, you need to also perform the shift rows completely individually, not at the same time. Means that one clock cycle and not this Sbox and the output of the mixed column are actually used to be stored here, but the shift rows is applied, which actually is realized by should be realized by a multiplexer. Means that the multiplexer selects which input is given to this column or to this state. But then what else is important is the add round key, and you know that okay, this column is actually is processed, and you should actually give the same add round key or same sub bytes to the implementation. But of course, if you implement this sub bytes and mixed column, you may also think that okay, I implement the Sbox and mixed column in a block RAM. Yeah, you can also do that. But of course, you add one more latency to the implementation per round, because you need to wait 1 clock cycle for the BRAMs, which realizes the Sbox and the mixed column together. Yeah. But at the moment in this session, we don't deal with the BRAM. I mean, this is a pure hardware implementation which can be implemented in ASIC and also in FPGA, and it's not a problem. But for the add round key, we can suppose that at the same time when a Sbox and the mixed columns are performed, then the 32-bit of the corresponding subkey is also given here. But this should be definitely synchronized with the key schedule and with the correct subkey, of course. And this is something that needs a particular care, because the key schedule or the key state should also be shifted in the same way. Yeah, and then otherwise the implementation doesn't work correctly. Now, for the key schedule and the key state, you have the similar matrix, or let's say the registers, where this column, the same column, is given as a 32-bit output, and then everything is again shifted and rotated. I mean, during this 4 clock cycles, everything should be rotated here, and you cannot update or cannot do the shift, you cannot do the key schedule because the Sboxes are used for the sub bytes. And of course, as I said, during the shift rows operation, then the Sboxes can be used for the G function. But this is something that we will see a bit later when we deal with the VHDL files. One important thing is about the shift rows. Now, the shift rows should be actually implemented prior to the sub bytes and mixed column. Otherwise, this column doesn't work. And the same actually applies for the key. Means that when the key is applied to this implementation, then the key, the 32-bit subkey, should be already the output of the shift rows of the subkey, because the shift rows is already implemented or applied in the software state, and then the subkey is applied. Yeah, and then the sub bytes should definitely have the shift rows operation, but then we have a bit of problem when we do the key schedule over the key state. The data module has the reset and clock, and then some other signals which are coming from the control logic, like do shift rows, do add round key, do sub bytes, and do sub bytes and mixed column together, and do key schedule. We need to talk about them, and we need to deal with them, how they work, and which clock and which cipher round they are actually active, and in how in which way, in which fashion. Of course, 32-bit of the subkey is given, and also another point is that the output of the key schedule, I mean 32 other outputs, means that the input of the sub bytes for the G function is also given here to this module from the key module, and then the output of the Sbox is also provided to be given to the key schedule or G function, to be the G function to be computed inside the key schedule. Yeah. For that reason, you see some signals like the key schedule subbytes and key schedule subbytes output. Now, how these flags actually work and what they are and how they are connected to the implementation, we need to get back to the sketch and see how it is actually works. Then we need actually a large multiplexer which takes the output of the add round key and output of the Sbox and output of the mix column. Each of them we should select individually, because during the normal rounds, the first round till the 9th round, everything is fine. The add round key, subbytes and mix column are performed, means that the output of the mix column is selected. But in other rounds, it's not like this. Yeah, for that reason, you can think of something like this, that the state is there, and for the entire state, not only the columns, then you need one big multiplexer, which actually selects based on these flags, where this selects actually the output of the subbytes, which is combined with the mix column, followed by the mix column, and also the output of the add round key. This is required for the last round, after the last round, when the ciphertext is going to be generated, because at the end we need to have the ciphertext, and the ciphertext is the result of every operation at the last round after the add round key, and then the result of that round key should be able to be stored in the state. And then subbytes operation, because in the last round mix column should be ignored. Then you need subbytes, and also you need the output of the shift rows. And as I said, there is another flag like do key schedule, and the key schedule, when the key schedule is 1, it means that the output from the input of the G function should be given to the Sbox. Now we have one instance of the Sbox 4 times, means that 4 times of the Sbox are implemented, and then the shift rows, and then the inverse of the shift rows. We will talk about this, why the inverse of shift rows is required. And then mix 1 column. Now this is just 32-bit input, 32-bit output, not the entire columns are mixed. And then after the instantiating them, here the register input is actually provided by the big multiplexer that we have just explained. That the plain text is given when the reset is 1, because you need to load the plain text, or the shift rows output, or add round key output, or subbytes output, or the mix column output. And then the enable of the register is also set like this, that either when we do the reset, or we want to do the shift rows, or the add round key, or subbytes, or the subbytes and mix column together, then the enable should be 1, means that the register should be active. But for example, not in the case when that due key schedule is 1. And this time we don't want to update the key, the data state or cipher state. We want to just update the key state. Now the shift rows is applied here easily, and then make this shift rows output. For the add round key, what you see here is kind of a shift register. It means that part of the register output is the register input, and then now the XOR means that we have 32-bit shifts. You see. And then of course we need to provide 128-bit input to be given to this large multiplexer. Here is, for example, the 2-bit output of the add round key, and then here the other part of the register is actually just shifted. You see here that the most significant part are just XOR'd, and then they move to the least significant part. For the subbytes input, you see that there is a multiplexer, whether we do the key schedule or not. If we do the key schedule, then the input of the G function is given to the Sbox, otherwise the result of the add round key, the result that we just talked about. And then this is given to the 4 instances of the Sbox. And then a Sbox output, the first part is provided, what you see at the top, and bottom is exactly the other 4 columns of the state that is actually just shifted. Now the output of the register is taken to build this shifting and the result of the Sbox. Then the instance of the mixed column, which is 32-bit input, 32-bit output. The Sbox output is given, or subbytes output, and then mixed column output is exactly similar to what we have seen for the Sbox, means that the mixed column just 32-bit output, and then the rest is just the content of the register shifted. What you see here is the output of the register is actually going to the shift rows, and the ciphertext is provided. This is what I have explained, means that at the end, when the cipher is performed, last round is performed, we need to do the last add round key, and then the result that is available in the register should be taken as the ciphertext, because we need the ciphertext in the full state, 128-bit, not, for example, 32-bit per clock cycle. But then shift rows is already applied there. Yeah, why the shift rows is applied? Because we need these shift rows to be applied to run the key schedule. Then what stays inside the register is the shift rows of the ciphertext, and we need to apply an inverse of the shift rows over the ciphertext to get the ciphertext correctly back. What is important is shift rows and shift rows inverse are actually for free in hardware, because they are just routing. Yeah, they just change the position of the bytes in 128-bit value, and then they do not add any logic to that. Yeah, then it doesn't matter if we have one extra shift rows or one extra shift rows inverse over the ciphertext, because it just changes the position of the bytes in 128-bit signal, not in the register. Yeah, I mean what is taken from the register is of course there, and then we just permute it and then generate 128-bit signal to give it as an output. Now we talked about this, and this is, as I said, this is the large multiplexer, but what you should consider is that we apply, or we do this column-based implementation to reduce the area, and then if the multiplexers are not done in a good way, the very large multiplexers will be used and instantiated inside the hardware, and finally the implementation will not be as small as expected. Therefore, you should pay particular attention on how to use the multiplexers. For example, here, part of this multiplexers or inputs of this multiplexer are the same, means that when we do the add round key or subbytes or mixed column, just 32-bit inputs are different. The rest means that 96 bits are completely the same for the add round key and subbytes and the mixed column. And then the synthesizer already optimizes this usually. Yeah, I mean, hopefully, unless or otherwise we see if it's not optimized very well, then probably you should write it down by yourself and then say, okay, the shifting part is actually based on some flags, and the rest is selected based on the other flags like the add round key, subbytes, and mixed column, and then hard code this 32-bit this 32-bit shift by yourself. Yeah, otherwise usually the synthesizer understands that and then optimize this in a good way. Now the key module has the do shift, because we do shift in 4 clock cycles, and then in 1 clock cycle per round we do the key schedule to update and construct the next sub key. And as I said, we need to provide the input of the G function to output to be given to the Sbox when the cipher is not using the subbytes or Sboxes. And then, of course, a normal register for that to store the values or store the state of the key. And then, as I said, we need to apply the shift rows first over the main key, the given key. And then this is the key shift rows. And then everything is done inside. I mean, the shift rows of the key is going to the multiplexer based on the reset. And then it's stored inside the register. Now, to keep the consistency between what is given to the key as the sub key output, a 2-bit part of the key, and then do shifting every clock cycle, that the shifting should be done, and then one clock cycle only the key schedule output. Yeah. Here, what is also important, when we want to apply the key schedule, we need to run the shift rows inverse over the register, and then get this result, which is actually the original value of the key state, and then give it to the key schedule. And then afterwards, the key schedule output is also given to another shift rows, to be the key schedule output applied shift rows to be stored in the register. Now, as I said, these shift rows and shift rows inverse are actually for free in hardware if they are implemented in parallel, and everything is actually fine. What is also important to say is that the key schedule, as we said, it receives the output of the Sboxes for the G function from outside. It means that inside the key schedule there is no Sbox or instances of the any Sbox. It means that the entire cipher works with just 4 instances of the Sbox and one instance of the mixed column. This shift rows and shift rows inverse, this is something which might be a bit, hard and complex to understand and follow. But this is one way to implement. It's not necessarily the best and the most optimum way to implement the AES using 4 instances of the Sbox and 1 instance of mixed column. You may end up or come up with another solution. Saying that, okay, this doesn't need to have those many shift rows and shift rows inverses, although they are for free, but they complicate the implementation or to understand the implementation. But you may now pay some extra clock cycles for that if you implement it differently, or no, you may also implement it in a better way with a better trade-off with respect to area and the latency. This is always like this, that there is a trade-off, and you have to find a way which suits the best into your application. Sometimes reducing the area consumption is important, but not at the price of having a very high latency or very low throughput. But sometimes it's also like this, that it doesn't matter how long it takes, and it should be the smallest implementation of the AES as you can provide, because for some cases the speed of implementation or the latency or throughput doesn't matter at all. What matters is just the area. I have to say that in nowadays in the current technology it's not the case usually, and you should be able to implement the full round-based implementation of the AES in almost every new design which is fabricated by new technologies like the 7 nanometer or 6 or 5 nanometer technologies. You have millions or thousands of or hundreds of millions of transistors or area to do that. Then there is usually not the problem. But what is important is that, okay, you should actually look at the utilization of your design. It means that you build something, and then you should look at how many LUTs and how many flip-flops are used. And of course, this is just for the FPGAs, because we are using Vivado for that. And then this, of course, includes everything, for example, the framework of the CMOD. What I can suggest you is then select, for example, the AES instance that you have as the top module, and then synthesize it. Now, what is important, please, you should not actually go further than the synthesis, because the constraint file is given for the CMOD 7 framework, not for the AES, and then you get, of course, complaints and errors. Then you do the synthesis when for example, the AES is selected as the top module, and then you run the synthesis here, and then the result of the synthesis will give you some estimation about the utilization. But of course, this is the utilization estimate. It's not perfect, because it might be reduced during the optimization of the implementation. But it gives you an upper bound. Here I have another implementation of the AES that we have done before, AES round based, using the block RAM, and to just compare the utilization. And I have one more design that I actually explain you a bit later what it is. And then I just set this also as a top module and do the synthesis. But we will talk about it a bit later. Let me just run the synthesis. Okay, good. Now it's doing the synthesis, and as I said, the utilization estimation after the synthesis, they are just the upper bound, because during the implementation, when you do the implement, the Vivado or any other synthesis tool may optimize better the implementation, and then finally the number of utilization or utilization percentage might be reduced after implementation or after implement compared to the synthesis result. Yeah, but usually this doesn't increase. I mean, usually it's not the case that after synthesis you implement again, then the utilization goes higher. But this gives you already a good estimation of the utilization that you have. But of course, the best way to compare two implementations is to compare them after the implementation or even generating the bit stream. But of course, they should have the same, let's say, the same framework, and everything must be roughly the same. And then only, for example, you change the Sbox and you just see which one is larger or which one is smaller. Now this is done and we can have a look here. Of course, you should ignore the I/O and buffer G at the moment. And this is the LUT and the flip-flop, 2607. And you may ask, why do we need more than 256? Because we need 128 flip-flops for the key and 128 bit for the state. And then now we have more because the RC, round constant, should be also stored in a register. And we have we didn't implement any counter. We just use the RC to control and see how many rounds we passed for the encryption and decryption. And now the other design is also synthesized or finished the synthesis. Now you can compare that you need, for example, 426 LUTs and some flip-flops, which is a smaller number, and then you need 10 block grams. And this is the BRAM implementation of the AES, 8 block grams just for the cipher, and 2 block grams for the key schedule. And this is another implementation that, as I said, we will talk about a bit later. But then you can also compare here the utilization, that you have 613 lookup tables and some other flip-flops, which is the same as the first design as we have seen. But then you can compare which implementation needs more area or which one needs less area if, for example, the latency and throughput of them are the same. Good. Now you can actually put them side to side, close to each other, and then compare in a better way. But as I said, this implementation needs 10 block grams. But I mean, some other implementations actually don't need block grams at all. But then again, we discussed about this, that the block gram implementations are dedicated to FPGA, and then you cannot actually compare one design which doesn't use the block gram with another design which uses some block gram. And in some implementations you have the opportunity to use the block grams, and in some others not at all. And the block grams are either not available or for example, this is not an FPGA implementation to use the block grams. And if you also examine this, you have to compare them in a fair way. It means that the same FPGA should be used. Now, a bit about the optimizing the Sbox. As we discussed, the Sbox is pretty large, and this is the largest part of the logic of the AES implementation. And then there were a couple of works. For example, David Canright implemented a very compact Sbox implementation of the AES almost 20 years ago. Yeah, and then it actually followed concept which is called the tower field approach, and we'll see how it works. But what is important also that he actually put his implementation on GitHub or on his personal webpage in the university, and then it was actually seen very well and very positively by many other researchers. I mean, he also generated a Verilog implementation that everybody could take and his webpage. And I have to say that he is already retired, but his implementations are available on GitHub. You know, you can take his implementation from the link which is provided in the slides. We can have a look at how this works and how this implementation is performed. First, having a look at the GitHub implementation. There is a C implementation, there is also Verilog implementation, and there are some other implementations like a Sbox mask and a Sbox mask correct. Please ignore them at the moment, and they are not relevant for our course. Just the Sbox, and you see this is a Verilog implementation including several modules that I will explain a bit later. But then the paper itself deals with some approach that I will shortly explain. But then you have to consider, or you should consider that this is a full report of his research. This research was supported by some agency, and this is actually the report of that research, which is pretty long compared to the paper, with more information and detailed information how this Sbox or this design has been selected among thousands of the other designs. The thing is, we discussed about this already, that the AES Sbox is actually designed like this, that if the X is the input, then first is given to an inversion function, and then another an affine transformation. And we discussed that this affine transformation is a linear function which is followed by a XOR or addition with a constant. The constant was hexadecimal 63, and then this was just the AES. Of course, the affine or linear and the XOR with the 63, this is almost a fixed part, and you don't have much options to reduce this part. But the inversion is the hard part, yeah, and this is the most expensive part. And if you, for example, write the ANF, algebraic normal form of the inversion, and you see that almost every monomial actually available or exists in this representation of the inversion. And then for that reason, if you just implement it using the ANF, it will be pretty large. If you ask the synthesizer to do it by a lookup table, it's also not as small. But what you can do, which is also given as a note in the AES Rindal original design, that you can implement the inversion using a tower field. And tower field means that instead of operating in GF2 to the 8, you can bring it back or bring it to a smaller field, that each of x0 and x1 are actually the element in GF2 to the 4. Yeah, and then you can say that x1 is multiplied by x. Yeah, I mean, this x is not a good notation. Let's differently write it. Let's write a, and then this is a0 and a1. And then each of these coefficients, a0 and a1, belong to GF2 to the 4. And we can write that a1 multiplied by x plus a0 is actually a. Yeah? And then, of course, this multiplication by x is again in GF to the 4 with another polynomial, irreducible polynomial. And this plus is, of course, is XOR, yeah? or this addition in GF to the 4. Yeah, this is the way, and of course this can be continued, means that then again another isomorphism here to bring it to a smaller field, that for example A00 and A01, and each one has 2 bits. And then again in a way that if you implement multiply A01 by x and then plus A00, you get actually A0. Yeah, and of course all these operations are in GF2 to the 2. This multiplication, also this addition, and in this way you bring it down, and of course you can bring it up. Every time that you want to calculate A0 from A00 and A01, you can do it. And then the thing is, in particular field, David Conrad showed that this inversion is just swapping between the inputs, means that this is for free, but of course you need many other multiplication and addition to build this. Means that some multiplication and some additions are required, and it's not for free, but just the inversion becomes for free. And of course this is just for one particular field, and it's not the same for every field, because this isomorphism and this changing from GF to the 8 to a smaller one, to the GF to the 4, and also even the smaller ones, they are not for free and they are not unique. It means that you have many options to do so. And then David Conrad checked exhaustively everything and selected just one implementation as the winner to report the smallest what he could reach. You see here in these figures exactly the same way of reducing and bringing down the way and performing the inversion in a smaller field compared to GF to the 4. And these are different ways, and even going smaller to GF to the 2, and this is the entire concept. Now, of course, if you are interested, you can read the paper, which is mathematically heavy, and you should have some knowledge in Boolean algebra to read and understand this. Is exactly fitting to the knowledge and expertise of David Conrad, and then because he was an instructor and of course professor in the university teaching these courses, and this was very well done by him. What is important is that David Conrad did this to reduce the area consumption, but the question is, how do we actually examine the area consumption if we don't have Vivado or something else and we check the area consumption? Many people first said that let's just count the number of gates, and then of course you can do that, but in some libraries you have super gates. You have super large gates like the AND OR gates or AND OR invert gates. For example here and OR, this is just one option, and everything together here just one cell, and then if you just count this as just one cell or one gate and then compare it with another implementation which doesn't use this concept or this cells, then it's not a fair comparison. Of course, there is other ones like the OR and invert, or AND without the invert, like this. And there are many different configurations, for example here like this, that one of the inputs actually doesn't go to the OR gates at all, and then you implement something like this, and then another module, and then just count the number of cells is not the best way to do. But then another thing is, you have a particular library, and then you look at the area of this. For example, you say this is just 2 micro, for example, meter square. Just for example. And another one is 2.2 micrometer square. And then you say, which one is larger, which one is smaller, and then how much area you need in silicon to implement the entire circuit. And then it doesn't matter which kind of cells are used and how many of these cells are used. But the problem is that if you have two different technologies, one of them, for example, 28 nanometer, another one 65 nanometer, then you cannot compare them like this, because of course the implementation in the 28 nanometer is smaller because the area consumption is smaller. Yeah, I mean generally for every gate. Then you cannot have a good comparison between two implementations. Then for that reason, something else was introduced, and then which should provide a fair comparison, but not necessarily. But it's almost better than any other solutions that we have at the moment. This is called actually gate equivalence, something which actually belongs to the area of the circuit, then divided by the area of NAND gate. Yeah? The gate equivalence, something like this, GE is written, gate equivalence. Sometimes also it's called gate equivalent, no? But I think it's gate equivalence is the correct one. And then what does it mean? I mean, you get the area of your implementation, how much, for example, is the area, for example, micro or micrometer square or something else in any unit, and then divided by the area of the smallest gate that you have, which is known as the NAND gate. Yeah, you may say, okay, the inverter is smaller, yeah, but with the inverter you cannot build the entire circuit, yeah, but using a single NAND gate you are able to build any circuit. Yeah, and then you also probably know that, and you have learned that an AND gate is built by a NAND gate followed by an inverter. Then NAND gate and NOR gates are the smallest implementation, usually nonlinear gates or two input gates inside a library. And the result of this will be gate equivalence, and then based on this you may compare two different implementations. But this is not necessarily fair. I mean, this is better than everything else that we have, but not necessarily the best. For example, if you have a library which has a large NAND gate, I mean, the NAND gate is not built in a good way and is super large, then the gate equivalence of every implementation using that library is very low, and it's good. No? You can say my gate equivalence is very low of that implementation. But if you use another library which has a pretty optimized and a small NAND gate, then the implementation doesn't lead to a good gate equivalence. You know, for that reason, it's not always the best to compare based on the area of the NAND gate, unless it's said that really the NAND gate is the smallest implementation that you may have. But how about the XOR, yeah, and 2-bit XOR and 2-bit NAND gates? Based on this, David Conrad just tried to implement everything, and then he counted the number of 2-bit XORs and 2-bit NAND gates as a factor to rank his implementations and understand which one is smaller and which one is faster, which is not a bad metric, but what we will see later, it's not necessarily the best for the FPGAs. Yeah? But in ASIC, you can reach exactly the same performance that he reported, but of course you need to avoid using the large and super gates. What is also important to discuss, I mean, there is a research in that area which is called, for example, in how many ways you can write actually Rindal, and there are some papers about that, and this means that the polynomial of the AES that we know and we use a couple of times is not mandatory actually for the AES. You can have another polynomial, and it leads actually to the same cipher, or let's say a cipher with the same security guarantees. Yeah? Suppose that you have the original AES, yeah, giving with a given key, you have X as input as the plaintext and the Y as the ciphertext. If you implement the AES using another polynomial, then what happens? You call this an AES prime, and then you can apply a particular function over the k and another particular function over the x or plaintext, And then if you apply another function over the ciphertext, you get exact the same result here. It means that they are completely equivalent to each other, and these functions, these t, h, and g functions are completely deterministic and fixed functions. They are completely independent of the inputs, and this concept is actually called dual cipher concept. It means that these ciphers are actually dual of each other. I mean, they are completely the same with the same guarantee, but then you just map the inputs and the outputs. I mean, the inputs, of course, the keys should be also considered as an input of this implementation, of this design. And this is the same when you apply the isomorphism at the start of the Galois, of the tower field implementation, what David Canroy did. And then there are multiple ways to do that. It means that you apply one function at the start and one function at the end, and in the between you don't follow the same polynomial of the AES, but then everything should be actually fine without any problem. I mean, just you bring it back. And then David Canroy checked almost everything, I mean, exhaustively, and then selected this implementation as the winner. Then if we look at the upper parts here, this XNOR and XORs actually, I mean, you can see that XOR and XNORs are used. You should keep in your mind that I talked about the AND and NAND gates. I mean, the AND is larger than the NAND, but it's not the same for example, for the XOR. XOR and XNOR usually have the same area. I mean, it doesn't matter if you use XNOR and XNOR, then you don't need to use XOR and then invert the output or invert one of the inputs. But you see here in this implementation, he always used the NAND operation. Here is the AND, of course, he negated the output. And this in this concept, you may tell the synthesizer that this is the NAND gate, but of course you can instantiate the NAND gate individually and force the synthesizer to just use the NAND gate. This is the way to implement this. What is also interesting to consider is that in his implementation, we can actually see here that we used in this implementation here the Canroy design. And then we will talk about this, that the Sbox and the Sbox inverse is used, but doesn't matter at the moment, we just use a Sbox. And then we have also the lookup table implementation of the AES. This is what we have used in other designs before introducing you to the Canroy Sbox. But then the idea is that, okay, the Canroy Sbox makes the implementation smaller, and then in another design, I use exact the same design. I just swap the Sboxes between the Canroy one and the lookup table one. We will talk about the best way to implement the AES Sbox in the FPGA later in the next session. But here, the implementations in the FPGA is like this, that the AES or AES Sbox of the design of the Canroy is not necessarily leading to the smallest implementation in FPGA. I mean, for that reason, we need to compare the utilization here. This you can see here that this is, for example, 613 LUTs just for the logic when the Canroy Sbox is when the lookup table based Sbox is used, and then we put them side to side. You see here that the lookup table based design needs 613 and the Sbox, the Canroy one needs 650. This, of course, as I said, this is just for the ASIC designs, and this is a good example to showing you that if something is suitable and efficient in ASIC, is not necessarily the smallest and optimized for the FPGAs. For example, now giving the full lookup table to the synthesizer to Vivado leads to a smaller implementation compared to those many efforts that David Canroy did. But this is not the only design. There are a couple of other designs, and for example, this one from roughly 10 years ago, which is a small depth 16 circuit for the AES Sbox. And the designers consider just the depth of the circuit, and not only the NAND gate, considering the entire and OR and XOR gates, and then just they wanted to reduce the depth of the circuit, of course, based on the fact to say that if the depth of the circuit is shorter, then the implementation is faster. And this is the paper that you can see. This is pretty short, just 10-11 pages. And the math is explained how they reached this. They have used some SAT solvers to find this depth 16 design, and this is one of the implementations that they have. For example, here this is a pseudocode, and these additions are XORed, and these multiplications by X, they are actually the AND operations. Yeah, I mean this not necessarily leads to a smallest implementation. You need to implement or say the synthesizer that you need NAND gates instead of the AND gates, and then invert the input of the XOR gates. But what CanWrite did, which is a nice way, is that you have the inversion, and then for the Sbox we said that you have the affine transformation, and then this is the normal way. But then if you want to implement the inverse of the Sbox, then you need to give the affine inverse. You have to give the input to the inverse of the affine before giving it to the inversion. Yeah, for that reason, then the affine inverse is given, and then to the multiplexer, and of course the output of the inversion and the output of the affine at the end also to another multiplexer. And then based on the encryption, whether you want encryption or decryption, then here you select whether the input directly is given to the inversion or the affine, the output of the affine inverse. And of course, for the output of this module, you can also select between the output of the affine and output of the inversion. And David CanWrite actually did this. I mean, you can see that there is just one bit for the inversion, for the encryption. What is also important to consider is that, as I explained, there are a couple of isomorphism at the start and the end of the inversion, and they are already combined with the affine transformation at the start at the end. Yeah, it means that he tried to combine these things because there are a couple of XORs, and these isomorphisms are all fully XOR. And then based on selecting which polynomials you select for the conversion from in this tower field, then they affect on the number of XORs and the operations that you have. This way, you may have a smallest implementation or even a bit larger implementation. These are the things that should be considered when somebody makes the Sbox and the Sbox inverse.